Okay, good morning, everyone. I think that's going to be enough time for everybody to log in, whoever wants to come and listen to this. Okay, so make sure that you guys have the syllabus and then you follow the schedule in the syllabus. So this week we should finish up Chapter 1 and 1A. So finishing up means that by the end of the week or by Sunday, you should have taken the review quizzes many times for Chapter 1 and Chapter 1A. After, of course, reading the chapter and taking your own notes. So let's get started with Chapter 1. Chapter 1 is just a basic overview. So it should not be difficult at all. It's just basic ideas about how computers work and what do we mean by C++ and the programming language. So as far as computers are concerned, computers are basically a bunch of silicon chips and a language written by humans that needed to be converted in order for that hardware, that silicon chips, to actually have some meaning to them. So humans can read and write in many different languages, but computers can only understand what we write in zeros and ones. So we need to have that conversion from something that humans can write to something that computers can interpret and understand. And in this class, we're going to be focusing on the language called C++. So if you look at history, there have been a lot of mechanical devices that allow humans to calculate and perform functions automatically. And if you look at what is it that we use today, if you Google or if you look up what is the Jacquard's weaving loom, those weaving looms are the ones where the loom was controlled by cards that had holes on them. And later on, in the 60s, those became punch cards. And from older programmers, you might hear about what punch cards were. But really, when you look at the history, you're going to see a lot of correlation between mechanical machines and the development of computers. So there are a lot of computers, and there are a lot of concepts about computers. And most likely what you heard about is Turing machine. You probably heard that terminology, Turing machine. But what is that Turing machine? Nobody really knew how to interpret Turing machine. It was a great idea. But how do you make a computer out of it? Not a mechanical or electromechanical computer, but a true binary computer out of it. And that was John von Neumann that came up with an architecture that made sense out of and implemented what Turing machine was. And John von Neumann's machine is basically what we use today, the Neumann architecture that we even use today in the more modern computers as well. Okay, so we'll talk about a little bit more on what that entails. But basically, let me see if I can draw something here for you guys. Okay, so if we have a machine, okay, and this machine has to perform a task. Now, computers can only perform single tasks. So then this machine can basically gather information. And as we gather information, in, let's say, in a loop, we are picking up zeros and ones in this loop. and that might represent data. When we're done picking up data, then we continue on, and in a loop we are picking up zeros and ones. That might be the instruction. So we can only do one thing at a time. So we pick up the data, then we pick up the instruction, and because now we have data and we have instruction, now we can perform whatever we picked up, what kind of information we picked up. And then we're back into our magic box, and then we can continue on picking up data, picking up instructions, and perform operation. So how did John von Neumann made sense out of this? Okay, so if we have a, let's see. If we have a machine, okay, and this is what we're going to call, let's say, our main function. I don't know if you remember it in the first assignment, you guys copied and pasted some text into the Visual Studio, and one word in that copied text was main. Main going to be our function. Okay, so now what do computers do? Computers take these code, and one at a time, one line at a time, they execute the code in it. Only one thing at a time. Now we cannot put everything in one single code. So if we have, for some reason, we have another code that we need to go to, we're going to call that a function call. What we do is we take the name of the function and whatever code is inside that function, let's call it function 1, and we load it on top of main. What that does is you are forced to execute the line-by-line instructions in function 1. When you get to the end of the function, then you return to the controlling code and you continue on executing. It's kind of like when you ask me a question, right? So I have something to say, but you raise your hand and you have a question, and then you say, okay, you need to stop with whatever you're saying, and you need to answer my question. So when I'm answering the question, I'm basically, that's my little smiley face right there. So I'm answering your question, and so I satisfy whatever your question was. And after I'm done with that, I go back and I continue on with my lecture. And then within my lecture, somebody else raises their hand. And then we take that question and load it on top of main again. So main gonna get sleep. So I cannot continue on with my lecture because I'm focusing on your question. But now I can focus on your question and I can answer your question line by line. When I'm done with that, I return back to my topic, whatever I was talking about. So let's say in main, we call the function 1. So somebody's asking me a question. Now somebody behind you also asks you a question. So you stop whatever you're doing and then you answering that person's question. So when you are answered that person's question, then you go back to your question, and now you are processing your question to me. So when you asked your question and I answered your question, then I go back and I keep continuing lecturing on a particular chapter. So hopefully it makes kind of sense that because of this stacking of a lot of different processes, we can handle each question one at a time. And that's what computers do that they can only work with basically one instruction at a time. So let's see. So that's how these computers work, these early computers work. So Mark I and ENIAC. Mark I was an electromechanic machine. So it has electronic components and it had a mechanical components to it. ENIAC was a hard-coding machine. So it still had electromechanical components on it, but programming was done with wires. So you had to plug wires into holes in order to make the program. So John von Neumann was the one that came up with a true digital computer architecture that we use today, and he was working with the government. So they created the computer to test nuclear explosions. So to predict, instead of blowing up a bomb, they wanted to test nuclear explosion effects. And then we had UNIVAC, was a commercial venture. So John von Neumann was working with the government. UNIVAC is more of a commercial venture. A for-profit organization created their computer. And then with the transistors and microprocessors, we had faster computing, basically. Okay. So categories of computers: mainframe computers. Mainframe computers, everything runs on one single machine, and what we call dumb terminals. The dumb terminal is basically connecting to these mainframe machines. Those are called clients. So these terminals do not have anything, no processing power. They only have a network interface card to connect to the server over the network, and it has a monitor and a keyboard. And usually you don't really provide the mouse because you don't do that kind of operation, but you can have a keyboard, video, and mouse connected to the computer that actually connects to the operating system. And then you have mid-sized computers for corporate usage, and then you have the microcomputers that we have in the home environment. Elements of systems, so you have hardware, CPU, main memory, storage, and all these different devices. So at the center of all, you have the CPU. Okay. Now the CPU, remember that I showed you that in order for us to process something, we need to get data and get instructions. Okay. So when we have data and we have instructions, we need to manage that. So how do we manage it? Well, when you have the CPU, you have two portions in two sides of the CPU. So you have the controller, okay, and then you have something called ALU, the arithmetical logical unit. It's hard to say. So arithmetics is what performs the operation, the control that allows you to get the data and get the operators. So you get the operands and operators, and the ALU performs the arithmetic operation. Now, in order for this to work, it needs to talk to memory. Okay, so we're loading a lot of things into memory, and it is your RAM, random access memory. We need the RAM because we need to load, we need to get all this information in order to perform arithmetics on it. Okay? And then you have a slower device, which is your hard drive. And that's where you store information for long-term storage. So it is non-volatile. If you lose power, information stays in or on the hard drive. If you lose power, RAM or the live memory is volatile. Volatile means that it will lose information, it will lose power. So the control works with inputs. So we need, normally we would have an input device, a keyboard, and we work with output, where you would have the output screen. Okay, so that's the basic structure of a computer. So we have control, arithmetic, logical unit, RAM, and hard drive. RAM is for short-term storage. Hard drive is for long-term storage. RAM is also called primary storage. Hard drive, your thumb drives, those are called, or CD, DVDs, those are called secondary storage. Input is whatever goes toward the CPU. Okay, so all this is what we refer to as a CPU. And output is what comes out of the system. Okay. So CPU, main memory, input-output devices, and secondary storage. So that means an operating system is a software, but the software needs to be controlling these hardware devices. The operating system needs to manage RAM or main memory. Operating system needs to manage the input and output devices. And the operating system needs to manage the secondary storage devices, or any storage device. So the CPU is the brain of the computer. It is your most expensive piece of hardware because that's what makes the computer so magical. That's what does all the work. Everybody else is just helping the CPU to perform its operations. Okay. So this is what most people understand from computers, but what regular users don't understand is how this memory works, how the memory operates. So here, when you look at a memory, okay, so the memory is a sequence of byte spaces. Okay, it's an array of storage devices or storage areas, and those storage areas are numbered. So in this case, let's say 1000 and 1001. So when we talk about variables later on, you need to understand that a memory is addressed, and on that address, on that particular location, there is space or storage area where we can temporarily store information. So let's say right now we have 1000, ID 1000, or address 1000. The memory contains 54. And the ID 1001, it contains the character A. So the main memory needs to be addressed, and then we're gonna address these memory addresses with our code to store information and retrieve information from. So that's going to be important to understand later on. So all these definitions are shown to you in the book, in the chapter. So read a little bit more into it, not from a user point of view, but really from the technical point of view. How does that really work? Not that I can turn on my computer and it works, or I know how to Google a website. So we need to look at it from a technical point of view. How does that really work? So random access memory directly connected to the CPU. all programs must be loaded into main memory before they can be executed. So a computer code or a program is not a code or not a program until we load it. The process of loading means that we actually taking the code, mainly what we wrote, we taking the code and we keep loading it, loading all the information into temporary memory. So this temporary memory will allow us to talk to the CPU, where the CPU will actually perform the operations and either take input or is going to display something on the screen. Okay. So programs must be loaded into memory in order to perform their operation. So main memory is volatile, so if power is turned off, data is lost. So the main memory is an ordered sequence of memory cells. Each cell has a unique location in main memory called the address of the cell. In Chapter 1, the most important thing going to be for you guys to learn definitions, the proper definitions, not your own words, but what is the proper definition. So secondary storage device, they store information permanently, and there are many different devices. For input devices, think about what is the input. How do you control the computer? That when you want the computer to do something, how do you control that? If it's a touch screen, it would be the touch screen that tells the computer what to do. If it's a mouse and you move the mouse around and you're clicking on the mouse, those are all instructions to the CPU that you're asking the operating system, you're asking the computer to perform something. And how do we know if it was performed? Well, through output devices. An output device can be monitor, printer, or secondary storage like your hard drive or your USB thumb drive. So software is a program that do specific tasks. Humans are very bad at doing things over and over and over again. Computers love that. Computers love the ordered sequence of instruction. Do this, 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 and this, and do it 5 billion times. And they're going to perform it exactly the same 5 billion times. And they're never going to complain about it. So that's why we need the software. So system controls the computer. Computer means the input-output devices, something called the interrupt request, IRQs, memory they need to manage. They need to manage file system. How do we access the file system? So all that the system program does. So the operating system monitors and looks at the overall activity and manages all the resources. So really the operating system you can call a resource manager. It manages memory, input-output devices, and storage management, or storage devices. Application programs are different from system programs. Application programs perform one particular task, like the application we use right now, Blackboard, Collaborate. It does great for communicating or presenting information to each other, but it does not do any kind of a file system management or those kind of tasks that the operating system is performing. So games are applications, spreadsheets, word processors, those are all applications. Those are application programs. They're not operating systems. So one thing we need to look at is binary and how computers work in a binary system. So let me go through these and then I'll show you how to convert between different bases. At the end of the book, you can also look up the appendix, and in the appendix, you're going to see a way to or learn how to convert between different bases. Okay. So analog signals are continuous waveforms. Digital signals are sequences of ones and zeros. So an analog signal looks like that, right? Like an audio signal. A digital signal are usually square signal. And then we can see where something means 0 and something means 1. So usually when you are on top, whoops, that's not, okay? So usually if you are on top, it's on 1. If you're on the bottom, it's a 0. And there's a time between. Because there's a time between, now you call those a discrete signals. An analog signal is continuous. So you cannot really see any difference between the data points because it's continuous. But with digital signals, you can measure the high voltage and the low voltage. And high is 1, low is 0. So let's say if there's a signal comes in, square signal, something like that, okay, based on the time, if you slice that up to time, this would be, let's say, 0, 1, 0, 0, 1, 1. So that's how the computer looks at the voltage that comes in, converts it into zeros and ones, and that's how they perform the operations. Machine language. A machine language is our instruction to the computer in zeros and ones. So the machine language is generating the digital signals that allow the computer to perform its operations. A binary digit is the actual 0 or 1. Those are the individual digits. A binary code or a binary number is a sequence of zeros and ones. So we'll remind me to talk about that if I forget. Okay. So a byte is a sequence of 8 bits. So in every byte there is 8 bits. A kilobyte is 2 to the 10th or 1024 bytes. ASCII characters, or American Standard Code for Information Exchange, is going to be important. Now if we go to the, let's say, the internet, and we just say ASCII code, okay, let's say, and we go to Google first. Okay, so let's do ASCII code. Okay, so the ASCII code, if you look at it, let's see. It would be nice to have a larger image that we can see. But anyway, so you guys can see that these there are many ASCII tables out there. So if you look at these ASCII codes, okay, let's say character A, capital A. Capital A is 65. So the characters that you type in, A through Z, the capital characters are different from the lowercase characters. They all have their ASCII representation, their ASCII code. Okay, so capital A is 65 in decimal, which means 41 in hexadecimal. Okay, so So that's what this is referring to. Let's see if we can, if I can explain this. Okay. Remember that one byte is 8 bits. That is 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the 4th power, 2 to the 5th, 2 to the 6th, and 2 to the 7th. Okay. So these are the placements for each one of the bits within a binary value. Okay. So what is 2 to the 1st, 2 to the 0th power is 1. What is the 2 to the 1st power? Is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th power is 16. 32. 64. And 128. Okay? This is what you need to remember. This is the basic understanding, or basic 8-bit sequence. So in this 8-bit sequence, okay, let's see if we can convert a number. What did we say what A was? Capital A was 41 or 65, right? Oops, I think we lost it. Okay. So it is 65 or 0x41. Okay. When you see a number and there's a prefix to a number, 0x means the number that you're referring to is a hex value, hexadecimal value. Okay, so what is 65? 65 is 64 plus 1, right? Everything else is 0. That's the simplest way. I mean, you guys can follow the book how to convert that, but I think this is the easiest one that you can see the components of a number. Okay, so let's see what is B then. B is, if 65 is A, B has to be, because it's sequential, right, ordered list. So that means it has to be 66. What is 66? 66 is 1 plus 2. 64 plus 2. Everything else is 0. So what is C then? C must be 67, right? So what is 67? 64 plus 2 plus 1. And everything else is 0. So then, what is D? 68. What is 68? 64 plus 4. Okay. So this would be the basic conversion. Okay. So what does the book say? Okay. Remember 1, 2, 4, 8, 16, 32, 64, 128. Okay. So let's say A is 65. Okay. So what we do is you take 65 and then you look at and say, does 128 go into 65? And you say no. And you write down 65 again. You go to the next power of 2, so you're going backwards. And you say, okay, does 64 go into 65? And you say, yes, one time. 64 go into 65 one time, and then you subtract the 2, and then you write down the remainder. And then you keep going backwards. Okay, so we were over here, now we are at 32. Does 32 go into does 32 go into 1? No. Does 16 go into 1? No. Does 8 go into 1? No. Does 4 go into 1? No. Does 2 go into 1? No. Does 1 go into 1? Yes. You subtract the 2, the remainder is 0. So when you reach the 0 remainder, then this is your sequence of zeros and ones. So capital A is represented in a computer as the number 65, and that 65 can also be represented as a hexadecimal value. Okay, so now what is a hexadecimal value? And you guys not going to have to do this on tests. This is more like information. Okay, if you look at the hexadecimal value, if you group 4 bits into a group, okay. Now here what you need to look at is 1, 2, 4, 8. 1, 2, 4, 8. Okay. So if you look at 65, 65 is 0, 1, 0, 0, 0, 0, 0, 1. Okay. Now what is that? The first 4 bytes, the first 4 bits, okay, is just 4. See, we only see a 1 at 4. Now when you look at the second group of 4 bits, here we only have 1 by the decimal place 1, so it's that is 1. So that's why 65 is the same thing as 41 hex. Okay, and you guys can watch a lot of YouTube videos or something if you are interested more in this conversion, but it will take some time, and you're not responsible for actually doing the hand calculations. But later on, it will be very useful if you guys would know how to do these conversions. Okay. Now, one thing that you can also do is you can use your calculator. Okay. So if you use your Windows calculator, okay, let's see if I can start it. Okay. So now here's your calculator. If you switch the calculator to programmer's calculator, okay, you guys can see the values in the display, but you can also see these bunch of zeros, okay, and that's going to be important. So let's say what is 65? Whoops. Let's do 65. Okay. Now here you can see it's 0. Ignore the leading zeros. So 0, 1, 0, 0, 0, 0, 0, 1. Okay. Now what is that in hex? With this calculator, you can just click on the hex button, and it shows you that it's 41. So you can see that the binary values do not change. It's still exactly the same. So decimal values or binary values or hexadecimal values or octal values, it doesn't matter. It is only for displaying to humans. So humans are easier. Humans handle smaller numbers easier. So a hex value or a decimal number, you can remember 65, but somebody would have a hard time remembering 01000001. But the calculator can help you double check if you are comparing or using something properly. Okay, so if you don't know how to what is a binary value or what is a decimal value of a binary, you can just click on the binary and start typing in, let's say 0011 0011 00111. And I don't know what that is in decimal, then I can just click on decimal radio button and it shows you that it's 1639. Or you can look at it, what does that mean in hex? In hex value, or base 16 some people call hex value, it's 667. Okay, but that's what that's how you can use your own calculator to learn about number conversions. Okay. So you need to look at the tables and then at least convert between unit of measure, understand the conversion between unit of measure. So that's going to be also useful, right? And here you would just do simple, let's say, what is 100 megabyte? How many bit is 100 megabyte? Okay, so you would just do a simple multiplication. Okay, so that would be megabyte. So 1 megabyte is 1024 kilobytes. 1024 kilobyte. Okay, so we can simplify the megabytes. So that means that's going to give us the answer in kilobytes. So how do we go from kilobytes to byte? Well, that's another multiplication. Okay, so we can multiply the result by something that we put the kilobyte in the denominator. So 1 kilobyte is how many bytes? 1024 bytes. 24B. That's going to cancel the KB, kilobytes. So continuing on, now we have bytes. So we need to see 1 byte is 8 bits. And that's going to cancel the B's. So that means 100 megabyte is 100 times 1024 times 1024 times 8. And that's going to give us the value in bits. Okay? So you use this table to help you with the conversion, basically. Okay. The Unicode characters. So when we talked about ASCII, okay, the American Standard, you have 8 bits per character. Now when you have Unicode, in Unicode, you have 8 bits plus 8 bits. So you have 16 bits. Okay. Now that's because the ASCII characters are fine for English language because we only have 26 uppercase, 26 lowercase characters, 10 digits, and a few special characters. So 8 bits is perfectly fine. But it was really using just 7-bit. So after that ASCII, in order to accommodate other languages, European languages or Spanish or German that has more characters, Okay. Then the EBCDIC was used, that now uses 256 characters. So ASCII was 127 character, EBCDIC is 256 character, okay? But now you have the Asian languages. The Asian languages require a lot more bits to represent their huge amount of characters. So that's going to be 2 to the 16th because of the 2 bytes. 2 to the 16th number of characters you can represent in Unicode. So Unicode was invented for what do you want to call it? Internationalization of computers, basically. Okay. So we talked about the whole idea that we have operators and we have operands. Okay. So the operands are also zeros and ones, and the operators are also 0 and 1s. So when you're loading something, you're multiplying something, you're storing something, those are all need to be converted in a way that the controller, the computer, the CPU can understand it. Okay. So an assembly language is an instructions of mnemonic. They represent something in a simplified way so humans can actually understand it. But then the assembler is the converter that actually takes what humans can understand and humans can write, and they convert it to a machine language. Okay. So let's see if I can show you how that actually works. What are these things right here? So if I share you guys my desktop, okay, not that. Okay. So you guys should be seeing my desktop now. And I need to go to XP, that's why I had to share you my desktop. Okay. Okay, so there's an operating system. It's called XP. Some of you might still remember it. Okay. So in this operating system, I'm going to go into debug. And in debug, I'm going to start programming. So this is, I'm at a memory area called 0AE7 at offset 100. So this is just a memory area. The memory area and the offset. So think about the memory area is the street, and the offset is a house address on that street. And I start typing. So let's say move A high low. I'm telling that at a particular address called A high, I want you to move in or set 0. All the bits, I want you to set it to 0. And I can do A low equal to 0. And then move BX 0. This is how you're clearing things. So when you look at a value, let's say in Excel, and you want to get rid of it, what do? You press delete. Here we are moving 0 into that area. And then I might say move A low 3 and move A high A. Now A is 10 in hexadecimal. Now let's just do 9. Or maybe maybe 5. So if you guys don't feel comfortable with hex values, you guys can still see what's going to happen here. So I'm moving an area of the memory, 3, and I'm moving 5 into another portion of that area. And then I'm going to add whatever is in A low and A high. So I'm not adding 3 and 5, I'm adding the container that contains those two numbers. Okay? And then maybe I'm going to jump to 100. So that's how you use the program, or this is very valuable programming skill even today. But this is not very human friendly. Okay, so let's see what really happens here. So, okay, remember I told you that we have only one instructions that a CPU can perform. Why is that? Well, if you look at here, okay, this is an instruction pointer. The instruction pointer says go to 102. What is 102? 102 says to move A low 0 0. So then it's going to perform that operation. And this is the AX, okay? And here's our BX. Those are called registers. Those are the registers that we load in order to later on perform something. So let's see what happens next. So now the instruction pointer says 104, and at 104 move BX 0. See, we are right here when I said move BX 0. The next instruction pointer points to 107. At 107 we say move AL03. Now here's the AX register. Before I launch this command, just make sure that you see all 4 zeros. So now when I type in and execute that command, move AL03, now you can see that the 3 is loaded into that area of the memory. Now here we say move A high 05. A high is the first 2 hex values in this, think about it like a bucket. Okay? So when I execute that, now you can see we have 5 and 3 in this memory area. And we are about to add the 2 together. So what happens? Let's see what happens. Look what happened here. We had 5 and 3. I did not have to tell the computer where to store the result. The result was stored in the lower half, AL, of the AX register. So we have a bucket called AX. This bucket is divided into high values and low values. When we performed 5 plus 3, the result was stored into the low half of the bucket. And now we have 8 in here. And then it says jump 100. Let's see what happens. See, jump 100 takes me back in the beginning of my code when I said move A high 0. And now, as you can see, we can go through the program again. Okay? We zeroed out, so the 8 was removed. Now AX is 0. So now we can move the 3 in there again. Move the 5 in there, add the 2, jump back, move A high 0, move A low 0, move BX 0, move A low 3, move A high 5, and add the 2 numbers together. So this is the step-by-step of what a CPU is doing, what your computer is doing. So we are adding values at a memory address, and we're not looking at what the content of the memory address is. We're just saying at this memory address and that memory address, add the 2 values together. And now we are jumping. So right now we are in an infinite loop. We cannot get out of it because we're always jumping back to 100. When we reach this line, we jump back to 100. So we're telling the computer to do this over and over and over again without telling the computer where to quit. So that's how computers work. Okay, I just wanted to show you that quickly. And this wasn't an animation. I mean, this is really how computers work. Okay. So that's what all this load business and the multiply and the store, what does that mean? That's what we used to have to type in. What I just showed you is the assembly language. Okay. So there are many different languages, and we're going to call these variables. That's the variable that's going to point to a memory address, and we don't have to worry about it. So as far as programming is concerned, it's going to be much easier. You don't have to be in that ugly environment when you say move AX and A low and A high, and it just doesn't make sense. To us, it's just going to be wages equals rate time hours. So the higher level programming languages makes it easier for humans to program. This is your first program, what you ran, but we didn't know what these lines meant, and we're going to learn about those. But this is how we write the code. It's much easier, much human-friendly than assembly language. Okay. So how do we execute a C++ program? We use an editor. That's why you have to have the Visual Studio. Visual Studio is going to be your editor to create the source file, the source program. Then we have a preprocessor. The preprocessor is right here, that it starts with a hash mark. Okay, so that's going to be the preprocessor. And then we're going to compile the code. To compile the code means that we create an object where the object is translated. What humans wrote, your source code was translated into a machine language that now the CPU can understand. Then we have linker. The linker that ties it to the operating system, where you are loading the when you load the actual code, the object that we compiled, okay, and then so the linker ties it to the operating system where this code is going to run, and then eventually we load the code. Okay, so the IDE do all this with a build and rebuild command. So to you guys, you just press the green triangle, and the green triangle did all this behind the scene. Only thing you had to do is just write the source code, and the source code was simpler than an assembly language, so it's more human friendly. This is a very important chart. You need to look at this chart, and every time you write the code, you kind of run it through your head, how that really works behind the scene. Okay, but this would be the most complete chart of how we actually write code. So first of all, what we need to look at is the analyzing. So you need to understand what you're writing for. You analyze what you are writing for, what problem you're writing for, and then you need to design an algorithm and then start coding. So we're not going to start automatically just code, because that would make us miss the first 3 steps. So then we're going to code, and then all this is done automatically for us. Okay, and it's going to show us some error messages, so we can look at it. Okay, but this is where we're going to do basic testing. Okay, this is what we do in design. Okay, and that's the coding part of it. So the first few chapters is dealing with the design of programs, and that's what we need to focus on. So this chart is very important for you to understand future chapters and to troubleshoot your code when you start writing your own code. Okay, and these are just explaining all the major steps in writing applications. Okay. So in this example, you have perimeter. First of all, you have to get a length and the width. Okay. So the length and the width is pointing to a memory area, someplace in memory. When we're going to ask a user to type those in, let's say 5 and 15. Okay. So there's going to be a memory area, let's say 1 and 2. So a variable is a named memory location. Okay, what does that mean? You only have to remember length. You don't need to remember where that length value is going to be stored. Okay. So perimeter is someplace else in memory. Maybe it's going to be a 3. So then what we do is we get the width value, we get the length, we add the two together, so now we have 20. We multiply it by 2, now we have 40. So that means we're going to put 40 in that memory location. So perimeter is another named memory location, now storing the value of 40 because we used the assignment operator. Okay. So the same thing that, let's say, the area. With area, we're pointing to width. With length, we're pointing to that named memory area. Now we are multiplying the two values, right? So area is somewhere pointing to the memory somewhere, let's say 0, 4. Okay. So now we are multiplying the two, and maybe area is going to be 75 after we use the assignment operator. We store that value in that variable. Okay. So try to go through all these examples in the book and try to look at it. What happens within the computer, where information going to be stored at. Okay, so this is an example of an algorithm with internal logic. Okay. So this is called total average, is a variable, and then we assign the value to that variable. Okay, structured, this is what you learn in this class. Okay, in this class we focus on structured programming, and the object-oriented going to be the Java class, which is COSC 1437. Okay, so that's going to be a different class for a pure object-oriented type of a programming. So you're going to basically learn both by taking 1436 and 1437. Okay. So it's just a bunch of definitions. That's all you need to look at. Okay. So hopefully it made a little more sense, or hopefully you guys have an easy time going through this chapter. What I showed you, you don't have to understand it for test purposes. I was just showing it to you to help you understand the concept. You're only responsible for whatever is in the chapter. And the way to find out what is it that you really need to know is by taking the chapter review quiz. Remember, you can take it as many times as you want, and that will help you understand if you know the chapter contents or not. Okay, you guys can take those as many times as you want. I'm not going to show you what you missed, but as you're taking it over and over again, you're going to understand the chapter more and more. Okay, so anyway, do you guys have any question after all this? Or just digest it and then try to bring in questions on Wednesday, or better yet, if you would have a question, Like I said, it would be better if you would post the question on discussion board so everybody would be able to see it, and hopefully they might answer your question. And so that way you guys can start developing a group kind of learning style, because I don't see much of a conversation on discussion board at this point. Okay. Anyway, we are 10 minutes over. Thanks for you guys to attend, and as soon as this rendering is over, it should be available in about an hour or two. I'm gonna have the link on eCampus for this video, and then you guys can rewatch some areas that did not make sense. Okay? So see you all next time.